So hello, today we are going to talk about dynamics of ship motion. And we are going to see three different things. Firstly, I will introduce the subject and tell why it's important to know about the dynamics of ship motion. After, I will talk about some equations linked with ship motion. And at the end, we are going to see how it's possible to ensure stability. So firstly, what is the topic of dynamics of ship motion about? So we know that in the sea there are a large number of forces that that can change the direction of the ship. So it's important to understand how the ship will react to the several forces it has been to the several forces that exist on the water, such as the wind, such as the waves. And that shows that it's really important to understand how the ship will react to them and what are the dynamics of the ship motion. The ship motion, the dynamics of ship motion is a complex process, because it's affected by multiple variables and multiple forces and also complex fluid dynamics. But some models exist, and for example, I will present the MMG model, which is used by Japan Towing Tank Commission. This model decomposes the hydrodynamics force and torque acting on the hull into those acting on, and the torque acting on the hull, and also it considers the interactions between the hull, the propeller, and the rudder. So here are the equations, and here are the several variables that are on those equations, but I will not develop more about those equations. So you should, maybe you're asking yourself, how can we obtain the equations I talked just before? So the different steps that we have to follow are, firstly, we have to start by putting Newton's law. After that, we will introduce the Coriolis and centripetal force and torque. So this becomes like that. Then we are going to decompose the forces, and it depends on the hypothesis we can choose at the beginning, but the forces can be decomposed on, and here to obtain this, we decompose the forces with the hull forces and moments, also the propeller forces, the rudder forces, the environmental forces, and the restoring forces. And this can be one way of decomposing the forces in which the ship is the forces that interact with the ship. So after we have to calculate the different forces, and we can obtain an equation that looks like that. Ships have 6 degrees of liberty, which are roll, yaw, and pitch for the rotational degrees of liberty. And there are also 3 transitional degrees of liberties, which are called surge, heave, and sway. There is also another mobility that can exist, but we don't. That is not good for the ships because it deformates the ship, and this deformation can occur when the buoyancy force is moved because of the wave. Because when we are at the crest of the wave, the buoyancy force is higher than the wave force, and that's why it creates this deformation. Now I'm going to talk about the three rotational degrees of liberty and discuss what are the risks and maybe the cures for this mobility. So as you can see in this drawing, pitch is movements of up and down motion of the ship. Here it goes up and down, usually like this. So there are some risks due to this mobility, which are damage, which are damage to slamming. And after there is also a yaw stabilization. So yaw is the movement quite well described in this picture, and it is really important to be. It is really important to control this movement because if, for example, if someone wants to move the boat through a direction, if you cannot control the yaw, then you cannot go where you want to, and so you have to find a good balance between stability and maneuverability. If not, you cannot turn your ship as you want to. So that's why it's really important to control this mobility. And one way of ensuring stability is adding this technology, which is called rotor. And I will explain a bit later how it works by comparing it to another technology that works a bit the same. So now we're going to talk about the roll stabilization. So rolling is the movement of the ship from side to side, and the risk of this is, if we don't control it well, is to have the boat capsizing, and different causes can lead to the ship capsizing, which are the wind force, the beam speeds. So it's important to control this mobility. So before talking about the different solutions to control this mobility, I wanted to talk about stability on ships, but we already did it just before my presentation. So maybe I can skip this part, but the thing, as Professor just said before, is that it depends on where the meta center is, the ship will be stable or not. So here it's stable because the meta center is above G, and here it's unstable because the meta center is beneath the J. So in this case, the boat can capsize, and we don't want that. So we have to find some solutions to deal with these problems. So now I'm going to talk about those solutions. So one solution is called stabilizer fins. The technologies. Can I jump here to explain something? So when the ship is turning because of a force, like for example the wind. So here is the ship that is rolling because of one force. It can be the wind, for example. If we add the solution with our stabilizer fins, I will explain how they work. So here's the
Draw bigger. Otherwise, other people cannot see from online. Also, you can use another pen. New pen. I don't know.
Right. Black is okay,
Yes.
no?
Yeah.
It's okay.
Je peux lécher dessus.
So here, if we look further, the thing is like this. So here, as depression is done because of the way the film is oriented. And this depression will lift against the roll to help to arrive to this configuration, which is a boat that is stable. And in this way, the thing will be oriented like this. And the depression is over there. So this creates a torque that goes against the wind force to reestablish the ship stability. So that's how the stabilizer things work, and the rudder has a similar operation. There's another mechanism that exists, which is called anti-rolling tank, and so it's water that is contained in the boat, and here we can control how many water will go from here to here. We can control the flow. So by controlling the flow, this will also create a moment that will stabilize the
So, now we have a antibody tank here. Stage. Rolling. Yeah. Natural rolling.
Bien sûr.
So if I
Il va stabiliser.
Comment ça se
Hein? Ici, on va d'un côté à l'autre, ça fait des bruits.
Comment
see again. So it is blocking the water movement by closing down the air chamber or something. So to lower down, or as Eva explained,
Carrément.
to reverse the movement.
Hmm.
This way. The damping is increased, so that rolling is rolled down quickly rather than just natural movement. This is natural movement.
T'as changé.
Stop. Right, that is the idea behind. Right, then another question.
Is quite effective. I think issues have rather study of space. I think
Yes, Eva explained about this disadvantage.
this is quite effective for the large ship. For the large ship, issues requires very very big
Tank.
calculations.
Right.
This is transferred to attach this tank to the large ship in the case of
Requires space and but which kind of ship needs such a technology? It is not so much required for cargo ships or fishing vessels. It is required for something like navy ships, cruise ships, passenger ships. Need a comfortable for the battleship or navy ship. They need a stable platform to launch missiles or landing over aircraft. So they need something like technology like this one to stabilize the platform. Then they need to make several ideas together, even though there is a cost. So it is depending on the need and cost. Also, you may push the water more, in a faster way, using a pump, something like that. This one is using only belt to close down the air movement inside it. But if you push the water more quickly, then there can be a little bit more help to reduce the. Right? This is a ship. This is a ship. Made of steel plate. Made of steel plate. This is a ship. Almost same. Right? And then we can say lightweight of the ship. Lightweight. Lightweight. When the ship is just constructed from the shipyard, lightweight. Still there is a weight. Right? So there is a balance between weight and buoyancy. Lightweight. So draft is shallow. Then I try to load cargo on the ship. Cargo on the ship. Ready? Cargo is loaded ship. Right? You see that draft is increasing, and also the freeboard is smaller. If you put another one, then no, it should be same, right? So then I can put a smaller load. Also, you can see that there is a hill angle. This part is more submerged because of the load balance. If you are thinking of container ships, loading containers, heavy container, empty container, you need to calculate to balance the weight. So I may put more on this side to balance the filling. Still okay? So the freeboard is decreasing. Then we have a wave here. Wave here, right? How it comes? You should know about the anytime there is a balance between weight and buoyancy, there is a key idea I'm trying to explain to you, right? Simple explain. We have a time for discussions.
J.
제호.